So today I want to first of all do a few examples and small problems. Rather, I'll just call them examples of matchings. These are basically problems from Douglas West, very simple problems. And the goal is I'll write just 2 words maybe, to get intuition and understand this maximal versus maximum better, because eventually we will maybe make some problems. I'll just prove a theorem which will show a precise relation, but right now it will not be, it will sound too just fancy if I say. So I want to first do examples which will do these things. So let's do this part first, and then I will move to a different kind of matching, which is maybe even more more combinatorial in some sense. Yeah. So we will see that. So first, let's look at some examples, some problems. So the problem number 1 that I want to do, and these are not even problems, they're just exercises basically to get intuition. Let's take this C11. Okay, so C11 is basically cycle with 11 vertices, and you know this cycle with 11 vertices. The question is find the, one second, sorry, find the smallest maximal matching. So how bad can a maximal matching be? Okay. Let's think about this. This can be framed as a problem if someone just maybe arbitrarily picks some edges, then what's the worst he or she can get? You can put some practical words in that and make a problem. But basically in this, so we want a maximal matching, but we want the worst maximal matching. So please just try this first, then you can think. No, so first cycle means obviously that these edges are there, but this doesn't define a matching by itself. Why should this define a matching? No, but that's not allowed. That's not a matching in our definition. Yeah, obviously those things exist, but yeah. So our matching is just what we had defined and basically just pairing away the vertices. Once you use this two, then you cannot use this and this again. Just the most natural sense of matching. Yes. So if you just take for 5 only, then what's the worst maximal matching you can get? But will it be maximal if you erase everything? Sorry? but will it be maximal? So you need to give me some edges which will make a maximal matching, meaning you cannot improve on that. Yeah. Yeah. So if you take 5, 4 and 2, 3, yeah. So this is certainly maximal. So let's note that down. So so M is certainly maximal, but can you give a smaller, can anybody, or is it possible to give a smaller maximal matching? Yeah, any maximal matching has to have at least 2 edges. Right. So that's a very simple observation. That's good. Yeah. So M is smallest maximal. M is smallest maximal. So for the case of 5, the answer is 2, right? So for the case of 5, the answer is 2. Smallest. So worst maximal matching. And what's the maximum matching? What should be the size of a maximum matching? Again, 2. Right. So maximum matching is also 2. So now, how do you answer this question for 11 vertices, or in general for n vertices? Mm-hmm. Okay, so let's try to write that. I can just remove this, not needed. This is not difficult problems. Once again. Mm-hmm. So, mm-hmm. Yes. So the maximum matching will certainly be 5, right? So maximum matching of Cn equals n by 2 or n minus 1 by 2, or you can just say floor. But then what should be the smallest maximal matching? So the answer was equal for 5. Both maximum and maximal are same. Does it continue? Think. Let's think. No, but these are all cycles. These are all cycles. Yeah. So sorry. Think a little bit. You'll get some intuition, some idea. Okay. Okay. So I'll wait for some reasons. Seems correct to me also. I don't know the answer. Seems correct. To try to give a reason. Good whatever reason. Yeah. Which are not chosen. Yeah, that's a good way to put it. Yeah. Not chosen, not saturated is the word, but yeah. So if you don't use this, why? Mm-hmm. We have to give a clear reason, like, or something, try to make it more clear. No, but it's not clear. So you have to say it, right? If one is not chosen in the matching, then you are saying that two has to be chosen. Right. That's what you have said. Right. But then if two is chosen, then is it possible that we don't choose three? No, one and three is not connected. One and three don't have an edge. It's a cycle. Is that? Yeah, that's a very simple reason, right? Exactly. That's good. Yeah, that's a very simple reason. So if two, uh, okay, let's see. So if three, so can we now skip four? We can skip four. Let's see. So what happens if we skip four? So let me just follow the same pattern. Then we can't skip five. But then we can't skip six. So we are getting some bad matching, and this is going to be maximal, right? Like till now, do you see any problem? No, but then if you don't choose three, then it will not be maximal, because if you're choosing two, then you have to choose three. All right. No, but something interesting is happening, which maybe we didn't foresee, right? The four can be skipped, and this 3, 4, and 4, 5 both can be skipped. Yeah. Right. So do you think you will get n minus 1 by 2 in this way? Yeah, something. But let's try to do a small completion of this example. So that's the thing. We were thinking that it's let's see, 9. So now we can um I mean we can break some patterns, right? We can take this and we can just skip the 7. No problem, right? You see, this is maximal. Let me. No, that is maybe not necessary. That depends on odd even. But sorry. Yes, that's a symmetric, right? But then we are getting something, right? We are getting 3, And this is a maximal matching because we cannot enlarge it. And this is not, this is not 4. It's not n minus 1 by 2. No, that's a little. I don't think that will. So yeah, Ritam, why will it call? Why can you enlarge it? Mm-hmm. Yes. If you would have chosen 4, 5. Mm-hmm. No. But what we have found is a maximal matching, and we are looking for the smallest maximal matching. You are finding a good maximal matching. I'm we're this maybe you are trying to find the best case, but we are trying to find the worst. And even so we were thinking that even small, obviously the best maximal matching is obviously going to be same as maximum. No. So improving upon in the most simplest sense, meaning that you cannot put in more edges. Yes, we cannot. Yeah, we cannot just. Yeah, you can obviously augment paths and so on, or what you said. Basically, that's an augmenting path. This what you were saying, right? Unsaturated, saturated, and then you'll take this two and you omit this one. Basically, an augmenting thing. And we have shown last time that that's the only way to enlarge. But that's not what we're not saying enlarge in that sense. Okay. We are saying enlarge the set of edges. We cannot enlarge the set of edges. It's an important thing to say actually because of something we will see later. But maximal means that, well, actually it doesn't should I should not say it because from the definition it is clear, because a matching is a set of edges. A matching is not a set of vertices, right? That one must, so maybe that's all, and rest you should, we all should try to interpret from there, right? So matching is, so because matching can be defined in several ways, but the very definition, the formal definition is it's a set of edges, obviously with some properties, with the saying that they cannot share vertices, but it's a set of edges to begin with, right? So when we use the word maximal for a matching, it means that with respect to that set of edges that you have taken, that's maximal, meaning that you cannot find a superset of that set of edges. So the definition is made in such a way that there is no controversy. Okay. But in some other sense, this is not maximal. It is not maximal in the sense of the vertices that are used. You can enlarge the set of vertices, and that's what you will get when you, for example, take this, and remove this. In that way, you see the vertices that were saturated remain saturated. So you are enlarging the set of vertices. And this is very crucial. This is used in some recent algorithms, breakthrough algorithms, this thing, that from any matching, when you're going, you can go to a bigger matching in the sense of vertices. The vertices that were used remain used, right? When you do this augmenting. But that's not in the definition of matching. So for this problem, that is not. Okay. So now it's a homework. So this is wrong. So for homework, now you can find the answer, I suppose, right? Just work it out, 2 small cases, you'll get the, yeah. So fine. Maybe I'll do it and say it in red. Please work this out. Mm-hmm. Mm-hmm. Okay. Yeah, and mostly it's similar, like n by 3 floor or something like that. N minus 2 by 3. Yeah, it will be roughly like that. But then you have to write a proof that this is in fact this worst maximal, right? I mean, if you don't, so you have to write a proof. Okay. Think about it. You can also use the fact that the complement is going to be an independent set, meaning that the vertices that are not used, they don't have any edges in between them. That is what it means, right? For the other part to be maximal, it means that the vertices that are not used, they shouldn't have any edges between them. Otherwise, you could enlarge the set of edges. You could use that, but do write a proof, because if you don't write a proof, then the intuition will not qualify. It means you won't get full marks. Okay, so yeah, so try to do it and submit it if you want to. Yeah, but the answer is mostly clear. Okay. So basically this tells us, just to get back, this tells us that basically the worst maximal matching also cannot be too small, right? Like the best maximal matching is n by 2, but the worst is n by 3. It cannot suddenly be very small. Okay, so that's the good thing about this. Algorithmically, that's a very good thing. We will make this formal. So basically, we are tending towards something like the any maximal matching or the worst maximal matching cannot be too bad. That will be the slogan, which we'll try to prove as a theorem. Okay, so this was a problem to get intuition. And for any graph, even the worst maximal matching is, I'll just say what it is, or not, let's, yeah, is not too bad compared to the maximum, right? Compared to maximum. In any case, we will prove. You have seen it in the case of cycles. When you take more graphs and you can just play with it, you will try to find worse maximal matchings there, and then you will see there also there is a relation. The maximum will be maybe 100. The maximal, you will see it will not be like 30 or 20, or okay, it will have a certain size. Okay. Now the maximal is something that can be easily found, and you just close your eyes and pick out edges, and when you pick an edge, just remove the vertices that you've used. Right? Yes, we can quantify. Should we say it, or just take more examples and try? Then maybe we should discuss it. Okay. Yeah, there is a quantification. Any graph, yes, that's the miracle. That's a very good thing. That is true for any graph. Okay, and this says something very significant. It means that, look, the maximal matching is trivial to find, right? There is literally nothing to do when you want to find a maximal matching. The maximum matching, we don't know how to find. We are kind of tended towards an algorithm in saying that you find augmenting paths and augment, and if you can't find, then it's maximum. But we still have to do a lot of work to give a good procedure to find augmenting paths and so on. But finding maximal matching is very simple. So this means that you can give a very simple algorithm to find a maximum, to find a maximal matching, and you will not get a maximum, but you will get a maximal, and the maximal is not too bad. So suppose you wanted 100, suppose the maximum would be 100, the maximal would be 50. Okay, so in a very simple algorithm will give a slightly imprecise answer. Huh? No, the maximal is easy to find. Right? That is that we can see maximum. No, that is just very simple to see. Is very easy to find. Yeah, if you just basically just pick any edge and just remove the vertices that you have, right, that you have used in that edge. So, and maximal is always trivial to find, right? Algorithmically, maximal is the simplest thing to find, and that's why what we did in trees, right? But in trees, the maximal was maximum. The trees is like very simple, right? It's not like maximal is not too bad. No, maximal is maximum in trees, right? That's why in trees you could find, I mean, from a graph you could find a tree just trivially. Just make sure that you don't get a cycle. But in this, find a maximal matching, you have to just take this, and when you take this, these two vertices, they are gone. They cannot be used anymore, right? So we remove this two also, because those vertices cannot be used. Then you pick anything else, and then remove the vertices that you have used, because remove the neighbors of the other neighbors of the vertices, right? Because they cannot, because that vertex, these vertices cannot be used now. And similarly, right, maximal is trivial to find. There's nothing to do. And combined with the fact that maximal is not too bad, you get an approximation algorithm, a very simple approximation algorithm. But for coloring, this doesn't happen. But we'll talk about that later. Okay. Yeah. So this is the thing. Okay. So let's, any questions? Any questions in this? So that we move to the next question then. Okay. So then let's move to the next one. Just thinking if I should do this or not. Just give me 1 minute. Yeah, so let's do it. So this is slightly theoretical. Okay. Let G be a graph. Okay, and M be a matching. So we can say this in several ways. And be a matching. We want to, we want to show that there is a maximum. There is a maximum matching M. Maybe I'll just call this N. A maximum matching N which uses all the vertices. Uses all the vertices means that edges involve those vertices. That uses all the vertices and maybe more, but uses all the vertices that were used in G. Sorry, that were used in N. So N is some arbitrary matching. It could be maximal also. But in some sense, we are saying that you can enlarge it to a maximum matching. Means enlarge the vertices. Just try to understand the question first, then we'll do a small example maybe. Let me try to prove this. So is the statement okay? So let's take a graph. And let's take a matching in this. This is certainly a matching, and is this, so first just answer a small question. is this a maximal matching? Is the green matching a maximal matching? Maximal matching? Is green a maximal matching? Right, right, right. So the green one is not maximal. You can include this, right? Okay, so now is it maximal? Okay, so now this is maximal. Now try to put the question in this setting and think. So now I'll just write yes here. I'll just ask the other question. This will also help you to understand the question better. Is green, is green a maximum matching? Yeah, if you can find something to augment into a better, yeah. If there are any, then yeah, if so. That's right. Yeah, 88765 can be augmented to get a bigger matching, right? So this is the answer is no. Okay. So if you just for a second see, you see again a maximal matching we have seen, it is not maximum. There is another matching which is maximum. Okay. So you see from the perspective of edges, or from the, if you consider a matching as collection of edges, which is the right way to consider it, because just saying collection of vertices doesn't say a matching, right? Because you don't know what edges could have been used. But from the, so the collection of edges was maximal, could not have been enlarged, okay? But it's not a maximum matching, okay? So in that sense, maximal is not maximum, and we have seen how to go to a maximum matching by enlarging. Is that okay? So this, maybe I just mentioned it. This green is the, now this is not the only maximum matching, obviously there can be others. This pink. So pink is a maximum matching. Now we come to the question. So let's call this N. And this to be M, and this is consistent with our question. Now see what vertices were used in N and what vertices are used in M in this example. That's right. That's right. So vertices saturated in N, let's write it. 1, 2, 3, 4, 9, 10, 5, 7, and 6. You see, these were saturated. Okay. And this was a matching, right? It was a maximal matching, but whatever, just a matching. We augmented some paths. We augmented found some augmenting paths and kind of augmented them. augmented some paths to get, or rather it's one path to get m maximum. Now you see, when you are augmenting a path, then the set of edges is not enlarging in the sense that you're kind of losing the one green edge and then, but the set of vertices is enlarging. The vertices, so whenever you augment a path, the vertices that were used remain used, right? So old saturated remain saturated, and some new saturated vertices. So the new vertices get used, now start coming in the picture. Sorry, 8 and 5. So does this prove our claim in the question? Can we write this reasoning for a general graph? Right. So we know this, right? That so let's this. So if you think about in this example, n was just an arbitrary matching. Just treat n just like an arbitrary matching. You can just take actually a maximal one because, but yeah, let's not complicate it. You take a arbitrary matching, and we know that given an arbitrary matching n, you can augment some paths, you can find some augmenting paths, augment them, and go to a maximum matching. And in this process, the vertices that were used, they remain used. That's it. Right? So you can just see the parallel. So, I mean, if n was arbitrary, so vertices used in n, you can just take anything. I mean, you don't have to. So now you can just take arbitrary, some k vertices, right? So how to go from here to a maximum matching? We know how to do this, right? Find augmenting paths and augment them. If you find more, find more, find more, keep finding augmenting paths, right? So find, let's say find an augmenting path first, augmenting path P1, augment the path with n, meaning you know what to do. So in n, something like this, you will maybe see this, and let's say this is the path in n. You will say, oh, okay. So let me, so this is an augmenting path kind of, right? So if you just find this in n, if it's not maximum, then you will find this, right? Because we know that if something is not maximum, then you will find an augmenting path. Does everybody agree with that? If something is not maximum, then there will be an augmenting path. This was the fundamental thing we proved. And this kind of makes this process of finding a maximum matching tractable, more easy, right? So maybe I can add that step. This was the key. Something whose presence means that it's not maximum, but something whose absence means it is maximum. So this is like both ways. So this kind of criteria, which is the augmenting paths criteria, it helps you to move forward. And it tells you that you can always move forward unless you have reached a maximum. So if n is maximum, then is there anything to do? No, then done. Then we can just go home. Right? If n is already maximum. If not, then there exists an augmenting path. This was the critical thing that we proved, that if something is not maximum, then there is a very simple path. There is a path in that which will tell you the story. There will be an augmenting path. That is the thing. If something is not maximum, there will be an augmenting path. We had shown this last time by comparing it with a maximum matching and kind of, uncovering an augmenting path, right? This is critical. This is the kind of characterizations you look for if you hope to find an algorithm for anything. Some context you want to find an algorithm, you want this kind of local equivalent characterization. Something which you will, if you don't see that, then you are sure that it is maximum. And that's the thing. Okay. So this will tell you to how to move forward, and that you will always end in the right place, maximum, not just maximal. If there is augmenting path, then augment. But then this we know, right? That in these, the vertices that were saturated remain saturated. That's the key, right? If you augment this path, this particular path here, using these, the vertices that were saturated remain saturated. This is just very, very critical, right? And obviously 2 endpoints also become saturated. And that's it. And so you have enlarged the set of vertices, right? And you keep doing this. And if you can't do this, it means there is no augmenting path, but that means it's maximum. And so you will find a maximum match. This process will end, obviously, if you find a maximum matching. But those that were saturated remain saturated, right? So from any matching, you can go to a maximum matching in some sense, right? By augmenting these paths. So you cannot enlarge the set of edges. So in that sense, maximal is not maximum, but you can enlarge the set of vertices. So in that sense, maximal is maximum, right?
If like new vertices are to be introduced, like we can say that there would be like some edges or it will remain the same.
No, the edges will obviously become additional. Yeah, new edges will come in, some edges will go away, right?
Yeah, so yeah, like in an augmenting path, if something is going, then that means that it's actually one more or
One more, always one more. That's very important, actually.
two are going away, then three are coming.
Yeah,
So
yeah,
that is the case.
yeah,
That's what I was
yeah. But
in an augmenting path.
yeah, that's right. Which is exactly if it's not maximum. But there is some difference. The edges are the edges, some new edges are coming, old edges are going, but vertices are not going away. That is obviously, we all see that, right? The number of edges increase, the number of vertices increase, but on a numerical level, that's both are same thing is happening to both. But on a more deeper level, or on just the next level, right? The set of vertices actually just becomes a superset, but the set of edges doesn't become a superset. That is the critical thing. Okay. Yeah. So you see, this is a very important point. And so in that sense, if this set of, so if n is a matching and you have the set of saturated vertices, then this set of saturated vertices is not maximal, all right? Because you can enlarge it. And if this set of saturated vertices, those vertices that are used in this matching n, if it is maximal, then the matching is maximum. Right? That is essentially what this theorem is saying. Right? So if n is a matching, and so some vertices are saturated, then there is a maximum matching which enlarges the set of vertices, right? Which means, now this means that if the set of vertices used in n cannot be enlarged, then it is itself a maximum matching. That's the same statement basically, right? So maximal saturated saturated, right? Vertices imply maximum matching. But this criteria is not good. I mean, this cannot be used well in the constructive sense, but it's, in theory sense, it puts this also in the same, under the same umbrella of maximal is maximum matching. So these two are the same statements, the problem and what I've said here, right? So if the set of vertices can be enlarged, if n is a matching and it has some set of vertices, then the set of vertices is not maximal, which means it can be enlarged, right, by a maximum matching. If it cannot be enlarged, then it means that it's already maximum. So in that sense, maximal saturated vertices means maximum matching. So then it means maximal is equal to maximum if you look at it from vertices perspective. But though that's a little ill-defined because vertices themselves don't define the matching. Yeah, there are several possibilities. Just telling the vertices is not enough, because if I just say 3, 4, and 5, 6, then you could have used 4 and 5, and maybe there was a edge here, you could have used this. So it's not, doesn't tell the matching completely. Okay. All right. So is everybody okay with this? Okay. Yeah. So